Hello, everyone, and welcome to my 6.6 video. In this video, got just a couple of things to go over, and then we'll get into a problem here. So I'd like to go over here really quick and just make sure to verbally announce as well that this Webwork payment stuff is now open, right? This drop date with refund for the course is coming up. That's September 28th. And so this is a university date. And then kind of after that, so this is about like the quarter way through the semester. But after that, right, if you drop, right, they don't refund you at all. And so a similar sort of deal for the Webwork. It's been free up until now. And same sort of deal. You kind of have to take care of the payment between now and September 28th. Otherwise, your account gets frozen and it's a little bit of a pain. And so, yeah, please do, don't have this even be an issue for yourself, getting locked out and all that sort of stuff. Take care of that sooner rather than later, I would recommend. Okay, so that's the first thing. The second thing is, right, I wanted to talk a little bit about what shows up in the 6.6 section as far as what we see on our formula sheet. And so I have pulled up here our formula sheet that we get on our quizzes and exams and everything. And in particular, so 6.6 is all about these inverse trigonometric functions. And so kind of course, as we go throughout the semester, a lot more of these will become more useful, up until the final exam where, you'll be able to use kind of any of these formulas. But right now, right, the inverse trigonometric stuff is really what 6.6 is all about. And so we are given kind of the base 6 right here, right? If you want to take a derivative of arc sine or inverse sine, here's the derivative. And likewise, if you want to take the antiderivative of this thing, right, 1 divided by root 1 minus x squared, then you're going to get arc sine. So kind of, even though they give you one version of this, remember, of course, that you can work it both ways, right? Either as a statement about a derivative or a statement about an antiderivative. So yeah, we actually get quite a bit from this section as far as what's showing up on the formula sheet. So that's quite nice. Okay, so with that, I would like to go ahead and do a problem. I have this one, and again, we're going to pretend that it shows up on a D2L quiz or exam, and this is kind of on the upper end of the spectrum. And so maybe now is a good time to pause the video if you'd like, try this problem on your own, see how far you get, and then we'll go over the results together. While you're doing that, I'm going to stop my sharing here and share on my iPad. All right. So here it is. And again, our goal is to evaluate out this antiderivative. You'll notice that quite often when I want to choose maybe a harder problem, typically the antiderivatives are more difficult than derivatives. So we don't see a whole lot of the derivative stuff. I guess, of course, with 6.4, when we were talking about logarithmic differentiation, okay, that one's a bit more difficult. But in general, I think antiderivatives are a bit more challenging. And so if I was, tackling this problem, not really thinking about where it's coming from or whatnot, one of my first things that I would try would be a u substitution, right? And kind of a common thing for a u substitution is to let u be equal to the entire denominator. And so I would probably try u is equal to 4 plus e to the 4x, calculate out du, and the derivative of 4 is 0. The derivative of e is itself. And of course, we need the chain rule, right? Because this is not just e to the x, it's e to the 4x. So I need to multiply by the derivative of the inside. So we're going to have 4. And then, of course, our dx here. And from this, you can see, I mean, maybe we could take a step or two farther here. But this integral is going to become something like, we're going to have division by u. Sadly, this is e to the 2x. It's not really e to the 4x, so it doesn't really communicate well with any of this other stuff here. And this dx, we could substitute in for du divided by 4e to the 4x. And so at this point, really, I'm starting to feel a little bit hesitant to move too much more forward with this, just because I think we're going to have a real hard time of getting solely u's rather than, x's, right? Remember, whenever you do a u substitution, you have to transform completely into u's from x's. And so I think that this is going to be a little bit challenging here. And even if we really push it and we really, try to get everything in terms of u's, I'm not sure if we're going to have a much simpler integral here. And so this is where I would really kind of back off and say, okay, well, maybe there's another kind of a more clever way of solving this problem. So let's go ahead and back up. Again, as of right now, u substitution is kind of our strongest technique for integration. So I do think we are going to use a u substitution in some form or another. But notice that it would be really nice if maybe this right here or something like this was our du, right? If that e to the 2x was absorbed in our du, I think that that would be quite wonderful. And so to that end, maybe you start thinking about, well, if that's the case, right, how could we rewrite this e to the 4x, right? And remember, e to the 4x, this would be the same thing. E to the 4x is the same thing as e to the 2x, right? Powers raised to more powers. So if I go ahead and I raise this to the second power here, then those multiply, and you get 2 times 2 would be 4. And of course, the x is along for the ride there. And so by realizing this, you say, okay, well, then that's just u squared. Okay, this is, actually standing a chance. And so I'm going to try, instead of our initial idea for a u substitution, I'm going to try e to the 2x here and kind of see what happens with this. Again, the main motivation why I thought that this would be a good thing to do is that when you calculate out our du, we get e, well, being a copy of itself. And then according to the chain rule, we multiply by 2. And of course, we have our dx here. So again, more or less, all of this stuff right here is going to be absorbed by our du, right? So if I go ahead and I rearrange just a little bit, I'm going to have 1/2 of du is equal to e to the 2x times dx. So again, we're trying to get that e to the 2x times dx. Maybe if that was our du, maybe this leads us in a good path. So in this case, okay, seems reasonable so far. And let's go ahead and rewrite this. So I'm going to have just a 1 in the numerator for the time being. And this is going to be 1/2 du. So I'm successfully transferring some of that stuff in. And then in the denominator here, we're going to have 4 plus. And again, remember we talked about that e to the 4x is going to be the same thing as e to the 2x just being squared. E to the 2x is our u. And so this is going to be u squared here. And so now this looks much, much simpler. And so I'm happy with this. I guess the last bit, we could start thinking, now we probably clearly see why this belongs in an inverse trig section, mainly that this is lining up pretty darn close with our inverse tangent or our arctangent. And so we do need to manipulate it just a little bit more in order to get it into this good form for arctangent. But hopefully you see, this 1 divided by, well, it's constant plus u squared. This is looking a lot like arctangent. Okay, so again, the formula for arctangent looks like it has a 1, right? So usually if it was 1 divided by 1 plus u squared, this would exactly be arctangent here, but we have a 4. And so we need to kind of think about, okay, how can we manipulate this so that we get this good 1 here? And so I'm going to go ahead and divide through by 4. And so when I divide through by 4, of course, right, 4 divided by 4 is going to be 1. But I can't just stop there, sadly, right? I also have to divide this other term by 4. And now this is me dividing by 4 in the entire denominator, right? So I've divided by 4 in the entire denominator. Now, sadly, that would change things, right? So if I want to divide by 4 across the entire denominator, that's perfectly fine, so long as, right, we have balance, and I also divide by 4 across the entire numerator. So I'm going to go ahead and divide by 4 across the entire numerator as well. And now this is just a rewrite. In fact, let's go ahead and take out some of these constants, right? We have this 1/2 that's been floating here. Now we have a 1/4. Let's take both of these out in front of the integral. And this is going to be 1/8, right? 1/4 times 1/2 is going to be 1/8. And so now we're just going to have a nice 1 there, and that's looking all right. Okay, so now, again, this is looking quite a lot like arctangent. You kind of have a choice here. I would recommend probably doing another small u substitution. Again, this is certainly on the upper end of the spectrum here, where we're going to have 1 plus, right, u divided by 2 quantity squared. right? So this u divided by 2, this is the thing that I would like to maybe call some other variable, just so it exactly lines up with our arctangent antiderivative equation. And so in that case, let me go ahead and I'm going to maybe make a v. So v is going to be just u over 2. So dv is going to be du divided by 2. Or we could say that, right, du is going to be 2 dv's. Oops, that's a horrible v. There we go. So if that's the case, right, so u divided by 2, I'm going to write v there. Instead of du up above, I'm going to write 2 dv, and everything else is along for the ride. So in fact, we could take this 2 now here and take it out of our integral so that we have 2/8, or this is going to simplify down to 1/4. Now we can evaluate this. The antiderivative of this is exactly arctangent. This is what we had from our formula. And 1/4 here. Now we need to start substituting back in, right? Instead of v, maybe I could put u over 2. And remember, that's not even finalized, right? Originally we had x's. U was originally e to the 2x. So instead of u, we could put e to the 2x. So this right here was an antiderivative. So this will work out well, right? Our goal is to find some number. And the way that we are going to get some number from this antiderivative is, right, we're going to plug in 0 and 1. Right, so I'll plug in 1 first, and then I'll plug in 0 and subtract those away. So yeah, this was all talking about an indefinite integral. So I'll just go ahead and finish that up. And so if we want to evaluate this from 0 to 1, we can just choose a c of 0 here. Oops, it's a large one there. E to the 2x divided by 2. And again, we're going to evaluate this from x equals 0 to x equals 1. And this will give us our final answer. All right, so if I go ahead and I plug in 1 everywhere, well, this is going to be e to the 2nd power divided by 2. And then finally, if I plug in 0 everywhere, well, e to the 0 is going to be 1. And so we're going to have 1 over 2 there. All right. And so lastly, I need to just carefully plug this into my calculator. And so let's go ahead and demonstrate that. Pull up my calculator here. I'm going to do 1/4 times arctangent. So this is going to be second tangent there is how I get to that. And then we're going to have e squared, so second natural log gets me to the e squared divided by 2. Close that parentheses, and then we need to subtract away 1/4 arctangent of 1/2. And again, actually, I should probably just be very specific, right, that there's multiplication between these. So I'm going to do second. Insert multiplication. So yeah, notice how I keep this all in one line. That way I'm not tempted to round or anything like that. And I get the final answer of 0.265 once we round to 3 decimal places. So again, if you round early, it's very possible that you'll make some mistake. Especially when you start multiplying by, 1/4 or other numbers, right? This will maybe change how many decimal places you need to round to. So again, I never recommend rounding early. It just seems to be a recipe for disaster, I suppose. I forgot it immediately. 265. So approximately equal to 0.265. All right, there you go. There is a difficult problem from our 6.6 world. Again, this comboed together a U substitution, and actually we ended up using 2 U substitutions just because the way that it lined up, it didn't exactly get arctangent. But at the heart of this, right, we needed to use arctangent. That's the new thing that we learned in 6.6, and that's what we needed to solve this problem. All right, thanks so much, guys. Have a wonderful day.